The journey to uncover cosmic rays began not with a giant telescope, but with a daring balloon ride high above Earth's surface. In the early 1900s, physicists were puzzled by a strange form of ionizing radiation that kept interfering with their sensitive instruments. The leading theory was simple. This radiation came from radioactive rocks in the Earth's crust, fading as you moved higher into the atmosphere. In 1909, a scientist named Theodor Wolff tested this idea by carrying a detector to the top of the Eiffel Tower, over 300 meters above the ground. To his surprise, radiation levels did not drop nearly as much as he expected. A few years later, Austrian physicist Victor Hess took this experiment to new heights, literally. In 1912, Hess loaded 3 precision electrometers onto a hydrogen-filled balloon and ascended to an astonishing 5,350 meters, high enough to see the curve of the Earth and feel the thin frigid air of the upper atmosphere. What he found changed astronomy forever. As the balloon climbed, radiation levels first dipped slightly, then skyrocketed to nearly 3 times what they were at ground level. Even during a near-total solar eclipse, when the sun's light was blocked, the radiation stayed strong, proving it could not be coming from our star. Hess had discovered penetrating radiation from deep space, cosmic rays. This groundbreaking work earned him the Nobel Prize in Physics in 1936, and it opened a brand new field of study that bridges particle physics and astronomy. For decades after Hess's discovery, scientists argued over what cosmic rays actually were. Some thought they were high-energy light waves, like gamma rays, while others suspected they were tiny particles of matter. By the 1930s, using cloud chambers that captured visible particle tracks, researchers learned the truth. Cosmic rays are mostly charged particles, not pure light. About 90% are single protons, the nuclei of hydrogen atoms, the simplest and most abundant element in the universe. Another 9% are helium nuclei, and the remaining 1% are heavier elements, all the way up to lead and uranium. These are not slow-moving particles. They are accelerated to mind-bending speeds, some reaching 99.999% the speed of light. Their energy levels are equally staggering. The most powerful cosmic rays ever detected carry more than 100 million times the energy of particles accelerated by the Large Hadron Collider, the world's most powerful human-made particle accelerator. To put that in perspective, a single ultra-high-energy cosmic ray particle can carry the kinetic energy of a baseball thrown at 100 miles per hour, packed into a single proton, smaller than an atom. These particles are so energetic that they can pass through entire planets, and they can damage delicate electronics on satellites and even pose health risks to astronauts traveling beyond Earth's protective magnetic field. Earth is fortunate to have 2 natural shields that keep most cosmic rays from reaching the surface: our magnetic field and our thick atmosphere. The magnetosphere acts like an invisible force field, deflecting many charged cosmic rays away from the planet. Particles that make it through collide with nitrogen and oxygen molecules in the upper atmosphere, creating massive cascades of secondary particles, called air showers. These showers spread out over miles, and by the time they reach the ground, only the most penetrating particles, like muons, survive. Every single day, trillions of these secondary cosmic ray particles pass through your body without causing harm, a constant, silent connection to the distant cosmos. But for astronauts on the Moon or on missions to Mars, there is no thick atmosphere to block these particles, making cosmic ray exposure one of the biggest challenges for long-duration space travel. NASA and other space agencies spend years designing, shielding, and monitoring systems to protect astronauts, because prolonged exposure to high-energy cosmic rays can damage DNA and increase cancer risks. This invisible threat is one of the main reasons understanding cosmic rays is not just a scientific curiosity, but a necessity for humanity's future in space. As scientists learned more about cosmic rays, the biggest question loomed larger than ever: where do these particles come from? Low-energy cosmic rays are easier to explain. Many come from our sun, released during solar flares and coronal mass ejections. But medium and high-energy cosmic rays are far more mysterious, and they come from far beyond our solar system. For years, the leading candidate for galactic cosmic rays has been supernova remnants, the expanding clouds of debris left behind when massive stars explode. When a star, 10 to 20 times the mass of our sun, runs out of fuel, it collapses in a catastrophic supernova, sending shockwaves racing through space at millions of miles per hour. These shockwaves act like natural cosmic particle accelerators, boosting protons and atomic nuclei to extreme energies over thousands of years. Observations from NASA's Nuster and Chandra X-ray telescopes have confirmed that supernova remnants like Cassiopeia, A2, accelerate particles to cosmic ray energies, solving part of the puzzle. But supernovae cannot account for the highest energy cosmic rays particles, so powerful they cannot be contained by the magnetic fields of our Milky Way galaxy. In recent years, new clues have pointed to even more extreme cosmic objects. Researchers, using China's Large High-Altitude Air Shower Observatory, or LHAASO, have found evidence that microquasars, small black holes, feeding on companion stars, could be the long-sought pevitrons that produce the most energetic cosmic rays in our galaxy. These black holes spin at nearly the speed of light, blasting out twin jets of plasma that act as hyper-powered particle accelerators. Beyond our galaxy, the most extreme cosmic rays likely come from active galactic nuclei, supermassive black holes at the centers of distant galaxies, and gamma-ray bursts, the brightest and most violent explosions in the universe. Gamma-ray bursts release more energy in a few seconds than the Sun will emit over its entire 10 billion-year lifetime, making them perfect candidates for launching particles across cosmic distances. In 2017, the Pierre Auger Observatory in Argentina confirmed that the highest energy cosmic rays are extragalactic, coming from galaxies tens of millions of light-years away. But even with these clues, we still cannot trace individual cosmic rays back to their exact birthplaces. The problem is that cosmic rays are charged particles, and they twist and spiral along the tangled magnetic fields that fill the universe. By the time they reach Earth, their paths are so scrambled that they arrive equally from all directions, leaving no clear trail back to their source. This cosmic magnetic maze is what makes solving their origins so incredibly difficult. Today, a global fleet of telescopes and detectors is working tirelessly to unlock the secrets of cosmic rays. On the International Space Station, the Alpha Magnetic Spectrometer, or AMS-2, has been collecting precision data on cosmic ray particles for over a decade, measuring their charge, energy, and composition with unprecedented accuracy. NASA's upcoming Tigris mission, set to launch in 2027, will study the rarest heavy element, cosmic rays, to learn more about the stellar explosions that create them. On the ground, the Pierre Auger Observatory uses thousands of detectors spread across the Argentine plains to capture the rare, ultra-high-energy cosmic ray particles that reach Earth. These missions are not just chasing a mystery, they are exploring the fundamental rules of the universe. Cosmic rays carry the chemical signatures of distant stars and galaxies, telling us how elements are forged and spread across the cosmos. They also test the limits of our understanding of physics, operating at energies we can never replicate on Earth. Every cosmic ray particle that hits our detectors is a messenger from the most extreme places in the universe, carrying a story we are still learning to read. What makes cosmic rays so special is that they connect the smallest building blocks of matter to the largest structures in the cosmos. They are a reminder that the universe is full of hidden forces and unseen phenomena, waiting for us to discover them. For over a century, they have puzzled and inspired generations of scientists, from Victor Hess's daring balloon flights to today's cutting-edge space missions. We now know more than ever about these particles, but their true origins remain just out of reach. Every new detection brings us one step closer, but the mystery still remains. What cosmic forces are powerful enough to create these ultra-energetic particles? Are they born in the death throes of stars, in the jaws of black holes, or in some exotic event we have not yet imagined? As we build better detectors and launch more advanced missions into space, we edge closer to answering these questions.